the HVAC technician is having difficulty running and lifting the compressor and the bracket if it is heavy weight. So for our target users, we focus to the efforts only, and we also follow the occupational safety and health at 1994 OSHA. So for our solution idea, which is to add the metal lifting, where it has to reduce the physical force required to lift the compressor, allowing for smoother vertical movement. And for the second one is pin and press, where it is efficiently reduce the internal bending moment on the link connection to achieve maximum rigidity and stability. And last, the wheels to provide portability and maneuverability, so the lifting tool can be easily moved and positioned in the working area. So this is the comparison that we made for the two products. So our product shows that it fulfills all the user needs, lift up compressor, main structural balance and prevent tipping, and able to move compressor easily. And this is the system architecture, where we use motor lifting as the lifting mechanism, and to tackle the stability we use a beam and truss, and for the portability we use the wheel and compact design. And for the other side, the functional diagram shows the flow of how the system works.
Okay, next, the design step table. So we have the three user needs, which is the lift up compressor, manufacturer balance and prevent tipping, and also able to move compressor easily. So these are the respective design attributes, design characteristics, design target. Before lift up compressor, promote compressor lifting. The design characteristic is the maximum lifting force, and the engineering target is 50 kg. For the main structural balance and prevent tipping, the design attribute is stability and structural rigidity. The design characteristic is center of gravity position and manufacture angle. The engineering target is the COD stay inside the base area, and the tip angle is less than 5 degrees. That's why it's able to move compressor easily, is portability and lightweight, maximum wheel capacity and the total mass of the lifting exclude. So the engineering target is wheel capacity 60 kg and the total mass of the product is less than 40 kg.
So this is for the first design analysis. We calculate the time rotation of the shaft motor. So we use the formula again is equal to number of revolution over time taken and in minutes. So we get for the time per revolution is 3.49 seconds per revolution, and we substitute into the formula and we get the 17 revolution per minute, and based on the rotation formula is equal to length over 2 pi r, which is the shaft of the radius 0.77 centimeter, and the rope length is equal to 4 meter, and we get 165 revolutions, and it will take 9.71 minutes to elevate 4 meter rope. So for the width, we use the formula, and we get the compression stress is equal to 0.49 megapascal, and based on the width allowable stress, we got 0.68 megapascal, 40% increase, and it is achievable. So for the rope, we use the formula, that formula, and we get 38.93 megapascal. And for the rope allowable stress is 15.57 megapascal, 40% reduced, and it is achievable as on the calculation. So this is the goal that we managed to lift. We want to manage to lift the maximum of the 4 kg loads, and for the testing, we applied 1 kg to 4 kg load, then record the time taken to lift the load, and we successfully lift the 1 kg to 4 kg load with the specific time, as the maximum for 4 kg load is 27 seconds. So this is the result of our testing. For the sample weight of 1 kg to 4 kg, as we can see at the graph here, it is linear, but to 3 to 4 kg is a little slightly a bit higher in slope. So is the second design of analysis where we are trying to find the central and center of gravity for our product design. So we use this formula and we get the central and the center of gravity at this point. We can see it's a little bit centered from our product. And for the second goal is we want our product to the field angle is not exceed to 5 dB. So based on our validation testing, we leave the 1 kg to 4 kg loads, and we get the testing result is below than 5 dB and not exceed the 5 dB angle. And then this is the last design analysis where we calculate the moment of inertia to find the greater moment of inertia for our product. So we find that the IXX dimension is greater than IYY. So we managed to use the base as 25 mm and head is 50 mm. So to get the strongest orientation to withstand the force, and the beam will set less than the loads. So for the mass of the product, we get the mass is equal to 6.64 kg. And then for this one, for the last step is able to move the compression by using the load of 10, 20, 30 and 40 kg. And this is the 40 kg of the load. So we managed to move the lift with the compressor.
So this is the video process prototyping. Including blending, cutting and finishing of the metal frame. So next, the validation video process that is explained by Aiman just now. The wheel act as the trolley function, and as we can see that the motor and the main frame is function accordingly. Okay, next go to the social environmental impact. So the problem is impact of the air conditioning unit typically weight 30 to 50 kg. Manual lifting increase physical strength and fatigue during installation. Limited manual handling contribute to long-term sustainability issues in air conditioning work practices. So what Liftex brings? Work sustainability. Motor assisted lifting reduce overall physical burden, promote more sustainable long-term work practices. Second one is the public safety. So control lifting speed and stable frame, reduce unpredictable movement, and parental safety and predictable operation. The last one is the environmental consideration. Metal frame of Liftex are recyclable. Next, economic impact. Why is at stake? So AC unit installation often requires multiple workers. Longer installation time reduce worker productivity and daily job capacity. With Liftex, lower operational cost, enables simultaneous lifting, reducing labor cost, higher productivity, faster setup and repositioning between sites. And the last one is the lower whole life cost, one-time investment, reduced across many installation. So for stakeholder consideration, primary stakeholder is small to medium scale aircon service provider company, reduce manpower and increase profit. For the secondary stakeholder, the air conditioning technician, reduce the burden, local metal shop, supplies the metal section, electric motor supplier, provide reliable motor with stable torque and electrical specification.
Your prototype, is it functioning now?
Yes.
Can show a demo? Try open it. Why you don't bring any load? That's my bag.
Don't worry.
No, but why you're holding?
You're supposed to fix on the frame, right? So it extends to the side, is it? What's the extension? Okay, so that's you extend it and it will sit on that compressor frame, right?
Yes.
And then is it just like hanging it, or are you going to like fix it, bolt it? Bolts. Okay, alright. The compressor, what's the weight of the compressor? 50 kilo. So you scale it down and just make it for 4 kilos. Okay. Show a demo. Why is it so slow? Because did you done your design analysis well?
Yes. But we have.
So this is what expected. You're expecting to be this slow, is it?
Yes.
Okay, but why you have to make it that slow?
So because basically the air conditioning installation require heavy load 50 to 50. So our target, we do not want to carry the load faster. We just want to lift the compressor safely.
So you think that's the ideal speed?
Yeah.
How do you choose the motor? Like for 4 kilos, right? So there must be the torque required and the power, the battery.
So basically, we calculate torque required for this load, and then we find motor that produce this similar torque.
Okay, so the motor, what you're looking? The spec of the motor.
Motor torque.
Motor torque. How about the power and then the battery?
Yeah. Basically, when we buy a motor, it's already stated the specification.
Okay.
Whether we need to use 12 volt battery or 24 volt.
So you're using battery lah?
Yeah, it's a battery.
Okay. Okay.
Alright, so you need is just to lift, right? Yes. Just to lift, that's the main one. Okay, stability, whatever the other thing. So can you go to your design step? Okay. Where is the weight? So you're doing it for 4 kg, not for the 50 kg.
No. To scale down, we use that.
Why you need to scale down?
First of all, the main reason because of the budget lah.
What budget? What you have here?
Yeah, basically
All steel bars. You couldn't make the right steel bars or whatever it is because you're fixing it on the thing, right? So only the motor maybe.
Yeah, only the motor, right?
Yes, the motor. But this small motor itself already cost 80 ringgit. This small motor itself.
Okay, fine, you scale down. Okay, nice. Anyway, because you had a chance actually to get the real prototype, only because you need only the motor, yes. Maybe the investment, like 6 of you, or maybe you provide the stuff, then you can get the real prototype. But anyway, let's say this one. So how do I know that how do you do the scaling so that I know if you work for the 50 kg and the stability for the real one and all those things? Because like this one, you said for 4 kg, right? So what is the calculation you did for the motor that it works for 4 kg? Because I don't see anything in your design analysis about the motor, which is the main component. This is the motor. Okay. What is the weight here?
For the calculation, we use for the 4 kg.
Huh? No. When you started here fixing everything, time, revolution, this, and then you did, I have the mass here, oh, the force is less than allowable, then okay. That's not the design. Your motor here, maybe if it is there, I don't know how much your sigma C compared to sigma allowable. Maybe you're over designed by 2 or 3 times. You don't need that motor. You should start again from the weight, and then go back and then find what is the spec of the motor. You don't specify the spec of the motor and then check if it works or not. This is common to all the 3 groups so far. And I remember very well in the presentation that I told you, this is the design, what you want to do for IDP. This is the other type of design, which is analysis, which we don't want IDP. And all you did, what we don't want. You do your spec, you do the calculation, you verify it fits or not. That's not it. Okay? You have to find the spec of the component. You don't assume it and then check if it works or not. Not only the other 2 groups of the mistake. So that's why here I don't see because this maybe even that the motor you have here for 4 kg, it might work for 50 kg if you over design, you know. That's why I said I don't see the scaling here. Anyway, so you said this and then I said go for the motor, then 4, it works. That's why maybe it's too slow, so it's not really like scaling. Anyway, so this one, it will be like they put the bracket first, yes, and then they put that one, and then they bring he will be there just when it comes, and they put it, right? Alright, so the validation, you did the weight, and you checked also the other 2, you have the other 2 like stability and why you do this 1 to 4 kg? For your test?
Because the motor only supports 4 kg.
Yeah, so why you did 1, 2? Is there compressors that they have different weights?
Yeah, basically compressor, the weight of the compressor is variously around starting from 35 kilo to 45 kilo.
But your design is 50. Why?
Because we want to really can use this for the maximum of the compressor, maximum load of the air compressor. So
For the heaviest.
yes.
Okay, if it works for the heaviest, obviously it's gonna work. If your motor lifts 50, then it can use 1 kg, right? Anyway, I don't see like the validation here why you do this. Again, design spec again, just wait and then, I mean, like I said, your design analysis is not correct for me. Right? So the number is 5 degrees, where did you get it from? Take angle 5 degrees, why? Why less than 5, not less than 10? Where do you get it from? So we said that rigidity, that's not related to rigidity. Rigidity will be maybe your moment of inertia and modulus, those are the ones that we call rigidity. Huh? No answer for that? Okay. And this one, the total mass of product less than 14 kg, again, what? Why 14? Should go for 40.3 or something. To be very accurate.
You don't have specific rule for that, but
No, but that, see, engineer, I told you again, engineering time, they cannot just fix on the top of your head. Right, it has to be from the user, if whatever, for whatever reason, like I said, maybe we have to get too tired that they can, within the standard, they cannot lift more than that, whatever it is. Or, If you don't get that one, then you go later from the standard maybe for health, whatever this, then there's a limitation of this. That you can specify by that one, but you cannot just, okay, let's pick 5 degree, if you pick 14, you pick that design. So how do you know that what the user needs or what will be approved by the authority later on? Okay? So that's why you have some number arbitrarily in the process, but they have to be really some logic behind the show. The first logic I told you, it has to be the user. If the user tell you, I want this mass or this, then halas. That's hard constraint. If not, then you go for the standard, for like the other guys, the current product it does this, I want to do better. That's again another way of specifying the user. Okay, I'll stop here before we grab too much. What is your group number? 4.
I would like to add a little bit, maybe suggestion. For your showcase, please bring a better dummy, not that plastic. Maybe like it looks like a compressor, so it will impress the judges better. And it's just automated, right? Motor only, right? There is no manual, right? I think it will be good if you have both, like motor and the manual as well. That's just my suggestion lah. That's it.
Okay. But like I said, your design analysis again, I think all the groups that you pass next to it actually. Because here you have to design actually the motor, the battery, the bars, the connection. Because that you put it like that, right? That one, you hang it to the bracket. Okay? How do you know that one will with the 50 kg, it will, I don't know, what did you do, welding or what? What is the job there?
Welding and bolts.
And bolts, right? So how did you choose that bolt? That under that 50 kg, it won't. It has to be designed. You cannot put in the bolt. You have to do the calculation of the formula, then you say, okay, this bolt can maintain whatever, 50 kg or 100 kg, then I can use it. The factor of safety of 2. So that's the design analysis in any component. You cannot assume any small component here. Everything has to be by calculation. Not only you, I'm talking to everyone. Okay? All right.
Okay, thank you.